Welcome to the Ventilator and Pulmonary Mechanics Chalk Talk series, where we're learning how ventilators work and how to work with ventilators. I'm John McManigal. Let's get started. For the last couple of talks, we've covered the details of how a ventilator works to get breathing gas into the patient's lungs, as well as the relationships between airway pressure, pulmonary pressure, and gas flow. We started to lay out the ventilator settings you'll have to choose: the mode, respiratory rate, tidal volume, PEEP, and so forth. The next step is learning how to adjust those ventilator settings to achieve the goals of treating hypoxic and hypercarbic respiratory failure. The short version is that we treat hypoventilation and its resultant hypercarbia by increasing ventilation, which is measured as minute ventilation, the product of tidal volume and respiratory rate, and we treat hypoxia by increasing the inspired oxygen fraction, abbreviated FiO2, and the mean airway pressure. If you're willing to take my word on those strategies, minute ventilation for hypercarbia and FiO2 and airway pressure for hypoxia, you can go ahead and skip to Lecture 9. If you prefer to work through the causes of respiratory failure and the reasons why we treat it like we do, these next two lectures are for you. This time, we're going to derive the relationship between alveolar carbon dioxide partial pressure and alveolar minute ventilation. Then, we'll dive into the alveolar gas equation. Finally, we'll use those equations to look at two causes of hypoxemia in a patient with completely healthy lungs. Those causes are hypoventilation and insufficient inhaled oxygen. You can find these derivations in any number of review articles and respiratory physiology texts, but if you're looking for a quick refresher on paper, I recommend this continuing education piece by Drs. Cruikshank and Hirschauer in Newcastle. It's published by the British Journal of Anesthesia. Cruikshank, of course, is also the author of an excellent textbook on mathematics and statistics in anesthesia. For the purposes of these derivations, we're going to start with a simple one-compartment lung model. That means perfect diffusion, perfect ventilation-perfusion matching, and no shunt. All of the cardiac output from the right ventricle winds up in this one massive pulmonary capillary, whereupon its dissolved gases diffuse into perfect equilibrium with a gas in this one giant alveolus and continues on to the left heart. In the next lecture, we'll look at imperfect diffusion, ventilation-perfusion mismatch, and shunt. We're also going to be assuming a steady-state system. That is, the body's consumption of oxygen and production of carbon dioxide are not changing dramatically over time, and the net amount of oxygen and carbon dioxide dissolved in the blood or hanging out in the alveolus might be high or low, but it's not actively changing. This assumption is generally true clinically, and it's why after you change the settings on a ventilator, you usually wait half an hour or so before you draw your next blood gas to let the system reach equilibrium. But it is useful to be keeping in mind the times that might not be true, which would be your big waxing and waning metabolic derangements like high fevers, sepsis, thyroid storm, serotonin syndrome, malignant hyperthermia, and that sort of thing. So let's begin with carbon dioxide. The strategy for these derivations is pretty simple. You look at where the gas enters and leaves the alveolus. Carbon dioxide is a great place to start because it only goes in one direction. Your lung is taking carbon dioxide from the blood and blowing it out of the body. This is also where our steady-state assumption comes into play. The total amount of carbon dioxide in the alveolus or dissolved in the blood is neither increasing nor decreasing. So every bit of carbon dioxide that the body is producing and passing into the alveolar gas has to be matched by an equal amount of carbon dioxide that's being exhaled. So do we know what these amounts are? It turns out we do. The amount of carbon dioxide being produced by the body, entering the venous blood, and entering the alveolus is the metabolic minute production of carbon dioxide, which we abbreviate V.CO2. Over on the right, I'm going to write in because that's the amount of carbon dioxide going into the alveolus every minute. Now, how about our expired carbon dioxide? That's going out of the alveolus and it's going to be the alveolar minute ventilation multiplied by what fraction of that minute ventilation is CO2, which is going to be the volume fraction of alveolar gas that is CO2, or F big A CO2. We know these two have to equal each other because of our steady-state assumptions. So our minute metabolic production of CO2 is equal to the alveolar minute ventilation times the alveolar gas fraction of CO2. Now, your alveolar CO2 fraction is just the pressure of alveolar CO2 divided by the alveolar pressure. So you can rearrange this whole expression as the partial pressure of alveolar CO2 is equal to 1 over the alveolar ventilation times your minute production of CO2 times the alveolar pressure. So in some ways, this already tells us what we need to know. The minute production of CO2 is going to be constant, the alveolar pressure is constant, so this equation tells us that our partial pressure of alveolar CO2, which is usually going to be very close to the partial pressure of arterial CO2, is inversely proportional to the alveolar minute ventilation. Let's go one step deeper into what we mean by alveolar minute ventilation. Alveolar minute ventilation is the gas moving in and out of the respiratory zone of the lungs, the alveoli and the respiratory bronchioles. It excludes dead space ventilation, which is air moving in and out of the trachea, bronchi, and conducting bronchioles because no gas exchange happens there. So alveolar minute ventilation is total minute ventilation minus dead space ventilation. Or, taken another way, that's your respiratory rate times the difference between your tidal volume and your dead space volume. Or, to use the more ventilator-centric abbreviations, respiratory rate times tidal volume minus dead space. So all of that goes to prove if you want to decrease your arterial partial pressure of carbon dioxide, you need to increase your respiratory rate, increase your tidal volume, or some combination of both. If you want to increase your arterial partial pressure of carbon dioxide, you need to decrease some combination of your respiratory rate and your tidal volume. We'll get into many more patient examples in lectures 9 and 10, but let's look at one now. Let's say you have a patient being ventilated with a tidal volume of 450 milliliters, a dead space of 150 milliliters, which are both pretty average for an adult male, and a set respiratory rate of 12 breaths per minute. So the difference between tidal volume and dead space gives you the alveolar volume of 300 milliliters, and by multiplying by the respiratory rate, you find the alveolar minute ventilation of 3.6 liters per minute. Now, let's say the lab calls you and says, "Hey doc, the arterial carbon dioxide on your latest blood gas was 60 millimeters of mercury. For my metric colleagues, that's 8 kilopascal. And so you say, "I'd much rather the patient's arterial carbon dioxide partial pressure be 40 millimeters of mercury, which is normal." So mathematically, your goal is to multiply your current partial pressure of CO2 by 2/3. Because we know alveolar carbon dioxide and alveolar minute ventilation are inversely proportional, we know we need to multiply alveolar minute ventilation by 3/2, or 150%. So there are a couple of solutions to doing this clinically. First, let's work out what 150% of 3.6 liters per minute is going to be. So our goal is an alveolar minute ventilation of 5.4 liters per minute. You could get that just by multiplying your respiratory rate by 150%. So if you ventilated this patient at 18 breaths per minute, leave their tidal volume alone at 450 milliliters, their dead space will stay the same at 150 milliliters, you'll find that this results in our goal minute ventilation of 5.4 liters per minute. You can also get there by leaving the respiratory rate alone at 12 breaths per minute, and instead increasing the alveolar ventilation volume by 150%. We'll assume for right now that dead space stays the same, It might change a little, but not much. So before our change, the alveolar volume is 450 minus 150, or 300 milliliters. We need to boost alveolar volume by half, or increase it to 450 milliliters. So our total tidal volume needs to be 600 milliliters. So one way to get to your target minute ventilation was to increase the respiratory rate to 18. Another way is to increase the tidal volume to 600 milliliters. And there are infinite combinations of ways to get to that target minute ventilation, but let's do one more example, which is to increase the respiratory rate to 15 breaths per minute and increase the tidal volume to 510 milliliters. All of these strategies you would expect to bring your arterial partial pressure of carbon dioxide down from 60 millimeters of mercury to 40 millimeters of mercury. We'll look at the various trade-offs involved in Lecture 9, but now we have the foundation of what our options are. And this is why it's important to know that the alveolar partial pressure of carbon dioxide is inversely proportional to alveolar ventilation. Now let's see if we can take this same approach for oxygen, which will give us the alveolar gas equation. Just like before, we'll look at where oxygen enters and leaves the alveolus. Oxygen coming into the alveolus is going to be alveolar ventilation times the inspired oxygen fraction, FiO2. And now, a little bit differently from carbon dioxide, oxygen leaves the alveolus in two different ways. You're exhaling some amount of oxygen, and obviously some oxygen is also diffusing into your blood to be used by end organs. The amount of oxygen diffusing from the alveolus into the blood is the metabolic minute consumption of oxygen by end organs. This is because under our steady-state assumptions, oxygen isn't allowed to build up in the blood, so the amount that enters the blood from the alveolus is exactly the amount that is consumed by end organs. And the amount of oxygen that leaves the alveolus by expiration is equal to alveolar ventilation times the fraction of alveolar gas that is oxygen. So we can rearrange this to get metabolic consumption of oxygen on the left-hand side of the equation and factor alveolar minute ventilation out of the right-hand side of the equation. Now, the last key step to making this derivation work is to remember the respiratory quotient R, which is defined as the amount of carbon dioxide produced for every unit of oxygen consumed, on a volume or mole basis, however you want to look at it. The respiratory quotient, you probably remember, is completely dependent on what fuel you're burning. So somebody on a completely carbohydrate diet has an R of 1, somebody burning proteins has an R of 0.8 or 0.9, and a person burning just fat has an R of about 0.7. Except in extreme circumstances, we assume that R is about 0.8 for most people. For our purposes right now, the actual number doesn't matter as long as it's constant, and it will be as long as the patient is on a somewhat stable metabolism. So we'll go ahead and substitute minute consumption of oxygen from the last equation into the denominator of this fraction. And for the numerator, we'll remember from our carbon dioxide derivation a minute ago that minute consumption of carbon dioxide is the alveolar minute ventilation times the alveolar carbon dioxide fraction. Now this just becomes high school algebra. We can rearrange this equation by canceling out the minute ventilation, so we have the respiratory quotient equals the alveolar carbon dioxide fraction divided by the inspired oxygen fraction minus the alveolar oxygen fraction. We can swap the denominators to get inspired oxygen fraction minus alveolar oxygen fraction equals alveolar carbon dioxide fraction divided by the respiratory quotient. And our whole goal here is to get the alveolar oxygen fraction on its own side of the equation. So now we can rearrange to alveolar oxygen fraction equals inspired oxygen fraction minus alveolar carbon dioxide fraction divided by the respiratory quotient. Finally, we multiply both sides of the equation by the airway pressure. So the alveolar oxygen fraction becomes the alveolar partial pressure of oxygen, The inspired oxygen fraction becomes the PiO2, and the alveolar carbon dioxide fraction becomes the alveolar partial pressure of carbon dioxide. So one more time, this is your alveolar gas equation. Alveolar oxygen partial pressure is equal to the inspired oxygen partial pressure minus the alveolar carbon dioxide partial pressure divided by the respiratory quotient. Because the inspired oxygen fraction is what we're usually modifying on the ventilator, you'll often see the equation written with a PiO2 term expanded out as FiO2 times alveolar pressure. And finally, because we usually measure FiO2 in the dry ventilator breathing gas, but gas is fully saturated with water vapor by the time it makes its way down to the alveoli, you need to subtract the vapor pressure of water from the alveolar pressure. So you'll often see the alveolar gas equation written this way. Alveolar oxygen partial pressure equals inspired oxygen fraction times airway pressure minus water vapor pressure, that quantity minus the alveolar carbon dioxide partial pressure divided by the respiratory quotient. I should also mention that we took one more shortcut in our model. We treated the inspiratory minute ventilation and the expiratory minute ventilation as the same number, but we know that's not quite right. If our respiratory quotient is 0.8, then we're only exhaling 8 units of carbon dioxide for every 10 units of oxygen we inhale, so each inhalation is a little bit bigger than each exhalation. You can redo the whole derivation to take that into account, and you'll see the quote-unquote long form of the alveolar gas equation in some books, but in reality it doesn't make a clinically significant difference, so everybody uses this one. So before we wrap up, let's look at the 2 causes of hypoxemia that come directly from the alveolar gas equation. In other words, we're looking at a nice healthy lung and pulmonary circulation, so the partial pressure of arterial oxygen is about the same as the partial pressure of alveolar oxygen. If that's the case, what can cause hypoxemia? The first cause is hypoventilation. If your alveolar carbon dioxide climbs, your alveolar oxygen is going to decline. So think about your otherwise healthy patient who came into the emergency room with an arm fracture but nice healthy lungs. They got a little bit too much narcotic pain medication, so now they're hypoventilating. The patient is breathing room air, which is 21% oxygen. They're breathing at sea level barometric pressure, which is 760 millimeters of mercury, and the vapor pressure of water at body temperature is 47 millimeters of mercury. Let's say their alveolar carbon dioxide is all the way up to 70 millimeters of mercury, and they have a normal respiratory quotient of 0.8. You can use a calculator just as well as I can. This works out to be an alveolar oxygen partial pressure of 62 millimeters of mercury. If you refer to a hemoglobin dissociation curve, this is going to be a saturation of about 90%. As an aside, this is one of the reasons I'm a big fan of getting people off of supplemental oxygen whenever possible, because in this patient, unless you ran a blood gas or happened to notice that he was getting obtunded, the only warning that you would have that his carbon dioxide level is rising is that his oxygen saturation is declining. On the other hand, if he were on supplemental oxygen and his FiO2 were 50%, you can plug the numbers into the equation, but his oxygen saturation would stay at 100% despite his carbon dioxide levels climbing quite high. So hypoventilation by itself, at high carbon dioxide levels, and especially when breathing room air, will cause hypoxemia. The second way to become hypoxemic with normal working lungs and no shunt is to be in a hypoxic environment with insufficient inspired oxygen. This is generally going to be mountain climbers, scuba divers with the wrong breathing gas, airplane mishaps at altitude, that kind of thing. But again, let's play with the numbers. So consider somebody at the Mount Everest base camp. The inspired oxygen fraction is still 21%. Barometric pressure, and therefore alveolar pressure up there, is about 403 millimeters of mercury. Vapor pressure of water only depends on temperature, so that's still 47 millimeters of mercury. And we'll even give this person a little bit of credit for hyperventilating, which they probably are. So we'll call their alveolar carbon dioxide partial pressure 20 millimeters of mercury. Once again, if you plug this into a calculator, you wind up with an alveolar partial pressure of 50 millimeters of mercury, and that will keep declining as you go further up the mountain. So this is why the vast majority of people who have summited Everest have done it while breathing supplemental oxygen. All right, let's sum up. Our goal in this lecture and the next is to understand the causes of hypercarbia and hypoxemia so we know how to correct them with a ventilator. This time, we prove that alveolar partial pressure of carbon dioxide is inversely proportional to the alveolar minute ventilation. We derive the alveolar gas equation, which tells us that the alveolar partial pressure of oxygen is equal to the inspired oxygen fraction times the alveolar pressure less the vapor pressure of water minus the alveolar partial pressure of carbon dioxide divided by the respiratory quotient. And finally, we looked at the two causes of hypoxemia that come directly from the alveolar gas equation, namely hypoventilation and insufficient inspired oxygen. Next time, we'll look at three more common causes of hypoxemia: diffusion limitation, ventilation-perfusion mismatch, and shunt. What these three will have in common is that the arterial partial pressure of oxygen will differ from the alveolar partial pressure of oxygen. Thank you so much for your attention. I'll see you next time.